Hello everyone, this is Pratima and welcome back to another experiment on frog's heart. In previous video, we have seen that vagus, that is parasympathetic innervation, has inhibitory effect on the heart. It stops the heart in diastole due to release of acetylcholine, which generates hyperpolarization by acting on M2 receptors on the cardiac muscle. If you have missed this video, link is provided in the description below. At this point, I request you all to pause the video and think what will happen if the vagus is stimulated continuously for the longer duration. Will the heart stop for that entire duration of the vagal stimulation? Will the animal die due to continuous vagal stimulation? Once you are ready with your answer, you can resume the video. Okay, some of you may have thought that yes, the heart will stop beating for that entire duration of vagal escape, and definitely the animal will die because of lack of blood flow to the vital organs. Others might have thought, no, there might be some mechanism by which heart can overcome the effect of continuous vagal stimulation, and that's correct. For both these questions, the answer is no. Heart escapes from the inhibitory effect of continuous vagal stimulation. This phenomenon is called as vagal escape. So vagal escape is defined as escape of heart from the inhibitory effect of continuous vagal stimulation. First, we shall quickly go through the setup required for this experiment, then the recording part, and finally we shall discuss the various reasons for vagal escape and its clinical significance. But before we delve into the topic, kindly read the disclaimer. Like previous experiment, electrical circuit is prepared by taking battery, Nif's hammer, primary key and EMTM in primary circuit. Secondary circuit is always constant. Then the heart is dissected as usual and both the vagi are dissected. Even though we need only one vagus for stimulation during the experiment, usually we dissect both the vagi and keep them ready, so that the other vagus is immediately available if necessary. Now the heart is attached to the lever and any one vagus is gently taken on the electrode. This makes sure that both the terminals of the electrodes contact the vagus throughout its stimulation. Now the normal cardiogram is recorded for the sufficient duration and vagal stimulation is started. As you can see, vagal stimulation immediately stops the heart in diastole. The time required for the heart to escape from this inhibitory effect varies from 15 seconds to 15 minutes. To conserve the recording space, we usually stop the drum but continue to stimulate the vagus, which is evident from the continuous movement of EMTM in this video. Recording is resumed when the contraction is detected. As you can note, at this moment the ventricle has contracted, but since the drum was stationary, we could record only the vertical line. After a brief interval, the ventricle contracts again, and this time we could capture the movement. Due to relatively long duration between the beats, we operated the drum intermittently, which unfortunately led us to miss another contraction. However, the lever movement is still observable. So we waited for one more contraction to be recorded and then we stopped stimulating the vagus. And as again you can note, heart gradually resumes to its normal rate as well as force of contractions. We continue to record this activity for some duration. So this was the procedure part. Now let's study the ideal graph. Here top tracing is EMTM and below is the normal cardiogram as usual. At this point vagal stimulation was started and the heart stopped beating. Now here is the first contraction despite the continual vagal stimulation. So we can say that this is the point where heart has escaped from the inhibitory effect of continuous vagal stimulation. In this case, after recording the fourth contraction, vagal stimulation was stopped. and heart has shown gradual recovery. At this point, once again pause the video and think, what are the causes for vagal escape? Whether this phenomenon is seen in human also, and if so, what is its clinical significance? Once you get the answers, resume the video. Okay, let's discuss the answers one by one. If you observe the graph closely, all the contractions recorded during the period of continuous vagal stimulation shows only the ventricular component of the normal cardiogram, and the rate of contraction is also less. So this rhythm is idioventricular rhythm. If you remember, we have got the same idioventricular rhythm after application of second staneous ligature. So the first reason for vagal escape is initiation of idioventricular rhythm. Why is it the ventricle that escapes from the inhibitory effect of the vagus and not the atria or sinus venosus? This is because, like humans, majority of the ventricular musculature of the frog is also not innervated by vagus. Second reason is, frog has vagosympathetic trunk. Hence, the vagal stimulation is also associated with simultaneous stimulation of sympathetic fibers. They release norepinephrine and exert stimulatory effects on the cardiac muscle. This antagonizes the action of acetylcholine and helps cardiac muscle to recover from the effect of continuous vagal stimulation. Another possible reason is prolonged vagal stimulation may lead to exhaustion of acetylcholine from the nerve terminals and diminishes the effect, which also helps in recovery. And the last reason may be downregulation of acetylcholine receptors, making the cardiac muscles non-responsive to acetylcholine. Coming to the second question, is vagal escape seen in humans? Yes, vagal escape is also seen in humans. In addition to the previous reasons, except norepinephrine release, Bainbridge reflex also contributes to the vagal escape in humans. Stoppage of heart due to vagal stimulation leads to accumulation of blood in the atria, and this initiates Bainbridge reflex. Now coming to the last question, clinical significance of vagal escape. In case of sudden and complete heart block, ventricles stop contracting and fail to pump the blood. As a result, person faints after 4 or 5 seconds because of lack of blood flow to the brain. Usually, Purkinje fibers or the ventricular fibers take over the function of pacemaker within 5 to 30 seconds, and ventricular contractions begin with the rate of about 15 to 40 per minute. This delayed pickup of heartbeat is called as Stokes-Adams syndrome. Regeneration of ventricular impulses because of this idioventricular rhythm is also known as ventricular escape. So due to this ventricular escape from complete heart block, blood flow to the brain is restored and the person recovers from the fainting attack. Thus, ventricular escape helps the person to maintain the circulation to the vital organs like brain and sustains the life of the person. Let's wind up the session by summarizing the important points. Vagal escape is the escape of heart from inhibitory effect of continuous vagal stimulation. Vagal escape can occur due to various factors including idioventricular rhythm, exhaustion of acetylcholine or downregulation of acetylcholine receptors. In humans, Bainbridge reflex also plays a significant role in this process. In frogs, release of norepinephrine by vagosympathetic trunk further aids in vagal escape. A similar phenomenon known as ventricular escape is observed in humans with Stokes-Adams syndrome during third-degree heart block. This mechanism is life-saving as it helps to maintain circulation to vital organs such as brain. So that's all for today. Thank you for joining in and see you in the next video. Have you not yet subscribed to my channel? Then go ahead and click the subscribe button and press the bell icon to stay updated about the new releases. If you like the video, give it a thumbs up and share it with your friends. Thank you for joining in and see you in the next video.